Hey, welcome back. It's Mr. Ankrum here again. I'm going to do another work example for our calculus class. All right. Let's look at a classic example of a variable force lifting a cable. So I'm going to draw a diagram. Just hope that it's a little helpful. Choose a different color here. Oh, these colors don't do too good on this background. Okay, the orange does. Well, let's just assume we have a cable that is hanging vertically, and the amount of force required, right, actually decreases the more it is lifted. And why is that? That's because there's less weight of cable hanging below as you lift it. Since this force changes along the way, we can't just use one value. We need to sum it up using an integral. So our work equals force times distance equation does not work for this scenario. But we do have an equation that we can use. Work is equal to the integral a to b of our function, right, our force function, dx. So here's the deal. We need to read the problem and see what information we have. You see that it's a 200-pound cable, and it's 100 feet long, and it hangs vertically from the top of the building. How much work is required to lift the cable to the top of the building? So we have our work formula. So we need to figure out what our force is, all right? Well, I have 200 pounds, right, cable, and it's 100 feet long. So my force, right, or the uniform weight of the cable, right, it means that we have 2 pounds per foot. Now, because we are dealing with less weight as we lift it up, we can't assume that that stays constant, but that is going to be a part of our force function. Well, we're going to let x represent the distance from the bottom of the cable to the top, right? So as it changes, x will represent what our new distance from the bottom of the cable to the top of the cable is, all right? So when I set up my function, I'm going from 0 to 100 of 2 times x. So our function is 2 times x, right? 2 pounds per foot, right? Because it's distributed evenly throughout the cable, the weight, times our distance at any given time, which we'll refer to as x. So it's pretty easy. So step 1 was finding the function. Step 2, set up our integral. Step 3, we want to integrate this. So when we integrate this, we get x squared is equal to 100, 0 to 100. And we just plug in, or we just substitute. And we get 10,000, right, pounds per foot, or 10,000 foot-pounds as our final answer. Now, we could have set this problem up a little differently. We could easily look at this problem and think of it a little bit in reverse. So same formula, we have work is equal to the same thing, same deal. But imagine we now think of the top of the building as our starting point, and the bottom of the rope is our end point, right? So this changes things a little bit, right? It doesn't change the fact that the rope is still 2 pounds per foot, right? So this is the weight of the rope at any given time, right? So 2 pounds per foot. And so, because it's evenly distributed. And so our 2 pounds per foot, right? So we distributed it evenly, right? And our distance from the top to the bottom, right? Before we called it X. But as we look at it from this standpoint, right? We can think of the total distance as being 100, but the length of the rope becomes, at any given time, 100 minus X, right? So what the total was, 2X, we can think of this as 100 minus X as our distance, right? So our distance is 100 minus X. So our new force function would be f of X equals 2 times 100 minus X. When we set this up, we're going to get the same result. I challenge you to try it out and see what you get.